Good morning, everyone, and welcome. My name is Andrew Minikowski, and I serve as the editor-in-chief of the Vermont Journal of Environmental Law. On behalf of our journal and Vermont Law School, I would like to cordially welcome you to our 2014 symposium, Cradle to Cradle, the Elimination of Waste. The Vermont Journal of Environmental Law is the designated environmental law journal of Vermont Law School, home of the nation's #1 environmental law program. Run entirely by current Vermont law students, the journal publishes 4 quarterly issues of relevant legal scholarship per year, maintains a bi-weekly environmental blog, sponsors a national environmental law writing competition, and of course, hosts an annual symposium focusing on a timely area of environmental law. Despite its astounding volume, the waste that human civilization produces often does not receive the mainstream attention afforded to other environmental issues, such as restoring clean air and water or safeguarding endangered wildlife. However, everything we do, even protecting the environment, produces some form of waste. Even as we gather here today to discuss reducing waste, we will collectively contribute to our society's prodigious waste stream. But we're not beyond hope. Our society is capable of producing less waste and reclaiming that which we have already created. Today we'll discuss this possibility in the context of energy, ocean, electronic, and food and agricultural waste. So sit back, keep your ears and minds open, ask questions, and join us for an exciting day of talking trash. But most importantly, when we part ways at the end of the day, share with others the ideas and knowledge that you obtain here today. It is now my exquisite pleasure to introduce the President and Dean of Vermont Law School, Mark Mohali.
Thank you. I'm Mark Mohali, I'm the Dean. First of all, welcome. For those of you who haven't been to Vermont Law School or just are coming from an agency or from the outside of another school, welcome to Vermont Law School. Welcome to Vermont if you're from out of state. To the waning days of our fall. First of all, I just want to say that congratulations to VJEL for putting this on. For those of you who aren't from the school, one of the things that sets this place apart from other schools is the energy and the self-starting nature of its students. And one of the ways that manifests itself. Somebody asked me here, well, what's the origin of this conference? And the origin is the students. Most of our conferences are conceived, they're conceived. The subject matter is conceived of by the students and organized by the students. And we think that that really makes a lot of what the school is. As to the subject matter, I think it's really interesting if you look at the program. Everything here has the word waste in it. But think how different each one of these fields is, really. Electronic waste, ocean waste, energy waste. Each of these is a completely different field in a way, and yet they all involve the word waste. And what's happening, this is what's happening to the environmental field in general, environmental law. What climate is teaching us is that everything is massively connected to everything else. And so that issues which used to be thought of as separate, in fact, are connected. So here we have in one conference, this waste word is causing us to take a slice across different fields. And it's my hope for today that those of you, particularly who are involved in one area, that it's a chance to sort of let your mind expand and take a look at commonalities with other areas. It's also my hope that in a decade or two, the word waste won't have any meaning. That it just won't exist as a word in that sense, in the sense that we're using it today. So, welcome. It's my pleasure to introduce Professor John Echevarria, one of the professors here, and one of the best known advocates for land use reform and for reform of our basic water schemes in the United States, and it's a pleasure to have John here at the school. John?
Well, I asked Mark before he came up to say it would be his exquisite pleasure to introduce me, but he offered some kind words, but he sloughed over on the exquisite. It's okay. So I am here because I am the faculty advisor to VGEL, which is an unbelievably light-duty position. This conference, as Mark said, was organized by the students, conceived by the students, and implemented with the most modest level of advice from me. That is characteristic of Vermont Law School, and from time to time they've humored me by giving me an opportunity to comment, but really my involvement is not needed and not all that welcome, actually. So that's fine. That's fine. It is part of our culture here. I too want to welcome the speakers and thank the speakers for putting in the time and effort to prepare for today and for your service today, and particularly for those who've come from a distance. This is really not what we call the leaf season. This is the beginning of what we call the stick season, and you have to be a real lover of Vermont to appreciate the stick season. I know very little about waste, and so I'm excited about today and learning more about this subject. The only insight I have on the topic is based on my Saturday ritual of going to the waste disposal site and the recycling center in my hometown, my new hometown in Vermont, of Stratford. I used to live in Washington, D.C., and in Washington, D.C., we had unlimited curbside pickup, and we had unlimited recycling pickup, and we had unlimited bulk trash pickup. So if you had an old couch, you'd call up the D.C. government, you'd say, I've got this enormous couch, will you come get it? And they'd come and get it, and it would all be free. It worked well from a consumer point of view. But I moved to Vermont, and we have this very elaborate recycling system. But we have a very, very limited and very, very expensive bulk pickup system. And in order to get rid of my trash, I have to spend $4 a bag to do that. So every Saturday I am annoyed, and then I am also reinforced in my conviction that market mechanisms sometimes work because I am generating a lot less waste than I used to when I lived in Washington, D.C. So that's the only insight I can offer to this conversation. So beyond that, I'm on the learning side of this. So let the fun begin. First panel begin.
Thank you, Andy, Dean Mohali, and Professor Echevarria for your kind introductions. I won't delay any further. We'd like to introduce our keynote speaker for today, Lauren Valle from the John Todd Ecological Design. We chose Lauren and John Todd Ecological Design because we felt their work sort of perfectly encapsulated the theme of the day about waste reduction and really waste preclusion, avoiding the creation of waste and sort of cutting it off before it's even there, and finding innovative ways to clean up after ourselves should we happen to make waste. So I'm just going to cue up Lauren's presentation here, and Lauren Valle, everyone.
I'm really excited to be up in Vermont. I live on Cape Cod, which is a beautiful place as well, but it's very populated, and Vermont is a really unique state, as I'm sure you all know, so it's just always nice to be up here. This is the trees. And I'm also really excited to share with you our work that we do at JTED. I think this is going to get this conference started off in a really positive note, because I think this work is really inspiring and is really about hope. So I'm the project coordinator at John Todd Ecological Design, and I'm going to we talk about ecological design. And so what I'm going to do in the next 40 minutes or so is give you kind of an idea of what ecological design is. That's probably a new concept for some of you. And talk a lot about our work and my boss and colleague John Todd's work. He was a professor at UVM for 12 years. He's lived up here. He's sort of a local. And then also give you another example of a different kind of land-based ecological design. We do a lot of water. I can get this going. I'm not sure that this clicker is clicking for me. Just bear with me, I have a little bit of a cold, I'm sorry. There you go. So what is ecological design? The concept of ecological design really goes far beyond the term sustainable design. When we talk about sustainable design, we talk about design that's considered to be less harmful or having less impact than a conventional practice. But ecological design, which is sometimes also referred to as regenerative design, you also hear the term biomimicry, which I'll talk a little bit more about, is a proactive design process where the design creates the space for and sets into motion an ecological process that mimics Mother Nature in a really intentional and measured way. So there's a fine balance in ecological design between controlling the system or environment that you're creating and working with and allowing these systems to interact with the natural world and establish themselves really in a far more complex and sophisticated way than we humans could ever imagine generating. So this is a conventional wastewater treatment plant, and this is a wastewater treatment plant that we designed in Rhinebeck, New York, at the Omega Center. So we're going to talk about how we get from the left to the right. So in this practice, we use our skills as architects, engineers, and designers in a radical new way. How can we design for the proliferation of life when architecture and engineering for the past few centuries has been focused on overriding natural forces we want to control? And this new design considers these forces as allies and seeks to design a context for them to exist in a way that's maximally useful for us. Howard Odum, who's considered one of the first thinkers of this kind of work, systems ecology, says that the inventory of the species of Earth is really an immense bin of parts available to the ecological designer. So, like conventional technologies, ecological technologies are intended to do work, whether to generate fuel, grow foods, transform waste, or regulate climates and buildings. But the difference lies in that a living technology is really made up of hundreds of thousands sometimes, or at least thousands of organisms, of living organisms that are acting in their own, with their own intelligence. So we're talking from microorganisms to mollusks to fish, plants, higher life forms, and then also they work in conjunction with sunlight and make use of the natural nutrient to waste biological processes that really all life is engaged with. So a good example of this kind of thinking is that human urine contains nitrogen, phosphorus, and calcium in a ratio that is essentially equivalent to fertilizer, to commercial fertilizer. And yet, all of our human urine, it goes into our waste treatment plants. But we actually have a resource, and so this is really this is a good example of what we think about when we think about waste. Is what is waste actually? It's often not really waste. We just have termed it that. And another interesting fact is that an adult produces enough urine to produce 50 to 100% of our food crop for itself. So our body is really in perfect rhythm with our waste and our nutrients. We can recycle them. So here's John. I want to talk about his work and our work together. As you can see, he's a very accoladed individual. and his work is getting some recognition now. So John, here's John in a rice paddy at the New Alchemy Institute, which is on Cape Cod in Falmouth, also where we are. And this is in the early 70s. And the New Alchemy Institute was a 35-acre research farm where a bunch of scientists had sort of a homesteading bent, and they got together and they designed a lot of closed-loop systems where they produced food and dealt with their waste and generated fuel. And they were very meticulous about their work, so they documented a lot of the work that they did and they published, which made their work spread fairly wide and is still influential in the world of closed-loop thinking today. So this is a dome that they designed in the Buckminster Fuller tradition, where they have a closed loop of trees, aquaculture, and then they've got their gardens. And then you see these series of clear-sided tanks sitting out in the field. And they're growing algae in these tanks to feed to fish. And you can see how this concept of these clear-sided tanks really gets into John's head and informs his work for the next 30 years or so. Here's a close-up. You've got fish in the tanks, and you've got algae growing. And this is an ark that was built by the New Alchemists on Prince Edward Island, which is producing food, including fish, cleaning waste, and feeding itself, all inside one building. And you see again the clear-sided tanks. This is schematic. And then this is the tanks, the schematic for the tanks. So this early work really paved the way for a wastewater and water remediation technology that we call the Eco Machine, also known as the living machine, which combines these sunlit tanks filled with aquatic life and other treatment environments, such as anoxic zones, which is a oxygen-deprived zone, and wetlands to treat wastewater and other wastewater. So the genesis of the Eco Machine was in a town of Harwich on the Cape, and here you see an unlined lagoon, septage lagoon, containing septage waste from households and small businesses. And this lagoon is sitting on sand, so it's leaking right into the town's water table. And this lagoon also contains 15 of the EPA's priority toxic pollutants, so it's pretty bad. And what John did was that he designed these 21 clear-sided solar tanks that connect together to form a river. And he also designed a marsh-based raceway. There we are. Oh, life. There we go. Between the tanks. So you have a river, you have these tanks, and then you have this marsh. And then into the tanks he placed hundreds of different forms of aquatic life that he gathered from half a dozen local environments, from puddles to ponds to marshes. And then after 12 days of the water flowing through the system, 14 of the 15 priority pollutants were removed to below detectable levels. And really only toluene was left in trace amounts. And that was 99.9% removed. And there's a catfish, which is eating algae off the side of the tanks. And so the effluent that you see here met federal swimming water standards. That's septage lagoon. And sunlight and a diversity of organisms, which had never occurred in these combinations before, which really self-organized within the system, co-evolved with the wastewater to provide a solution to come back into stasis, because that's what Mother Nature wants to do. It wants to find its stasis and wants to heal itself. And then another early work that John designed was also in Harwich, and this is the Flax Pond. And this was a technology we call the restorer, which kind of co-evolved with the Eco Machine. So the Eco Machine is a standalone technology that is enclosed. The restorer is an in situ technology, meaning on a water body. So a restorer is a floating plant raft that combines or supports masses of suspended roots with aeration, as well as anoxic zones within a water body. And so you can see, well, let's talk about the Flax Pond a little bit, sorry. So the Flax Pond is a 15-acre pond that had been heavily impacted for decades by leachates from an adjacent landfill and also septage. And in 1989, the pond was closed to recreation and fishing because of contamination caused by 78,000 gallons per day of leachate that was entering the pond. So the pond had low oxygen levels, was full of high coliform counts, excessive sediments, and organic pollutants, including all the organic compounds. So this restorer was anchored on the pond in 1992 and circulated 100,000 gallons per day of water drawn from the bottom of the pond. And you see the first 3 cells. There you go. The first 3 cells were filled with a semi-buoyant pumice rock that supported a benthic life environment, including clams. And then the final 6 cells supported over 24 species of terrestrial plants. So you see the plants on the sides. And so we're really talking about plant roots as an environment for the kind of bacteria that is going to metabolize these wastes. So the more plant roots and the more mass you can generate, the more of an environment you're going to have for this life, for organisms that want to really decompose these contaminants. And so for the decade that the Flax Pond Restorer was operating, the pond maintained its biological health, despite the continued onslaught of waste into the pond. Ammonia levels in the sediments did not increase. The pH of the water in the sediments hovered around neutral. Dissolved oxygen increased, and most importantly, there was 25 inches of sediments digested in 5 years by the restorer. So this is sort of the beginning of this technology in the 80s and the 90s, and John then coalesced these principles of ecological design, which I'm not going to go into at length right now, but if you want more information, I'm more than happy to get you everything you need to understand all of this. But he really understood, okay, there's some rules that we're operating by. And he continued to design. So this is Vermont. This is a plant in Burlington, Vermont. And this is a facility that he built next in the early 90s, mid-90s, that is located, it's adjacent to the actual waste treatment plant in South Burlington. And so wastewater is flowing from an anoxic reactor into 4 aerobic reactors. And then we have dense plants that were maintained on the surface racks. So then the waste then flows into a clarifier. There's a lot of wastewater terminology. Sorry to load you up, but and then the clarifier also had floating plants on it. So you can see this actually is very beautiful. These are one of the aerobic tanks. So this system was biologically diverse. There was over 200 species of vascular and woody plants that were evaluated for their effectiveness and suitability for wastewater treatment. Their ability to tolerate sewage, the extent of the root zones, disease and pest resistance, and the ease of management. And another really important thing that happened at Burlington was that they produced plants of value, so plants that could be used for restoration, that could be sold, and also a lot of fish. There was over 100,000 fish in the system, carp, ornamental fish, and then also bait fish. So they weren't just treating wastewater using biology, they were also creating an economic value. Shot of the tanks. And the wastewater that they were producing met regulatory standards for tertiary treatment. And I wanted to quickly put this slide up because what came out of South Burlington, this is at the Valle in Vermont, and this was a design for an Agro park. And so you can see that we have a whole bunch of waste loops. And this was partially built, and then the project never actually went forward because there was Indian remains discovered on the site. But you can see how this wastewater treatment really, you can include a variety of organisms and outputs. So then the next system I want to talk about was in Berlin, Maryland. It was a wastewater, it was a lagoon at a Tyson chicken processing plant. And so in the late 90s, the design of the restorer that was used in the Flax Pond evolved into this kind of linear restorer design for use on existing or new wastewater treatment lagoons. So this technology combines the benefit of the small footprint tank-based technology with really the simplicity of constructed wetlands. So this was a system that was installed in 2001. This lagoon there's 9 million gallons of waste in this lagoon with 1 million gallons per day flowing through. And there's 12 140-foot restorers that run across the lagoon and that were secured to the banks that really created this kind of serpentine S-shaped flow through the lagoon. This is, you can see the construction, the foundation. So 25 native species of plants were installed on these racks on the outside edges of the restorer. And the roots of these plants provided surface area and nutrient support for microbial communities. They had some nutrient uptake, and the shade they provided inhibited suspended algae in the lagoons. Water was treated also with fine bubble linear aerators that were installed at the bottom of the lagoon. And this treatment was 1/4 of the cost that Tyson had investigated. So they had looked at many other companies, and they chose to go with ecological design because it was a lot more economical for them. This system reduced electrical energy use in the lagoons by 74%, and there was a significant decrease in sludge production. So previously they were wasting 8 hours of waste, releasing 8 hours of sludge per day from the lagoons, and after the installation, sludge was wasted just 1 hour every few weeks. And this allowed Tyson to come into compliance with their regulators for their wastewater effluent. And it also was very beautiful. So this is another project traveling around the world a little bit in China. This is in Suzhou. This is a canal in Suzhou, China, which is one of the biggest, or an up-and-coming city in China. There's 6 million people in Suzhou, and the city empties its commercial wastewater and sewage into an 80-kilometer network of canals throughout the city before these canals empty it into a river. So obviously these canals are a health risk for the city's inhabitants and threaten the livelihood of the fishing communities downstream. This is an outfall, a sewage outfall. So what we did, this was in 2002, we installed a restorer on the canal. and used over 12,000 plants composed of 20 native species. And this was constructed with a walkway down the center. And this really became a prized recreational area for the community, as well as meeting water quality goals that the city had set out. So we saw nitrogen reduced to below 15 milligrams per liter. And again, we're talking about the root zones, and the fabric media creates kind of a baffle for treatment. Is what's achieving this treatment. So there was no more floating solids, there was no more odor, and this really just drastically improved the aesthetics of the neighborhood. There was an engineer that we worked with from China who saw this system as a child and spent her life, the rest of her young adult education, figuring out becoming an ecological engineer, because she had lived on the Valle Canal and saw firsthand the impact that this kind of technology had in her community. So this is a really exciting project. Here's a close-up. So back to the US. This is a more recent project. This is a canal in Grafton, Massachusetts, so in central Massachusetts. And this canal is emblematic, really, of a lot of waterways in the US, and especially this is on the Blackstone River. So Blackstone River is considered really the birthplace of the Industrial Revolution in the United States. It runs 45 miles from Worcester to Providence, and there's a lot of mills along it that were built in the 1800s, and particularly there was this one mill called the Fisherville Mill, which was constructed in 1832 as a textile factory. It first produced cotton textiles, later tool and dye, and finally lawn furniture and foam rubber. It closed its doors in 1986, so it was open for over 150 years. In 1999, a huge fire burned it to the ground, a 23-alarm fire, releasing massive asbestos plumes into the air, and the fire left behind toxic rubble on top of really an already degraded environment. So the site underwent a 5-year cleanup effort where much of the materials, including two 20,000-gallon storage tanks, underground oil storage tanks, were removed. But what couldn't be removed from the site was a heavily degraded canal that was choked with this bunker C crude oil that was in the storage tanks that had been leaking. So this crude oil leaches into the canal with every rainstorm. Here you can see the canal. So in 2006, an interagency and interdisciplinary coalition got in touch with Todd Ecological Design to see if a version of the Restore technology could be a solution for this canal, for the treatment of this canal. So while we had experience treating many tricky contaminants and high-strength wastes, this bunker C oil was a new challenge for us. So we designed a pilot study that began in 2006. Here's the pilot study, and added to our ecological treatment train cells of mycelium, of mushroom fungus, known for their capacity to break down petroleum hydrocarbons. And after a year collecting data on the pilot, we saw that these hydrocarbons were being degraded by over 90%. So we scaled the design up. And here's the actual greenhouse in Grafton. So what you can see is it's a 4-part system. Within the canal, we have a technology called a sediment digester, which is really just an HDPE pipe filled with media that is very heavily laden with bacteria that begins the oil digestion. And then we have the mycelial bins within the greenhouse. So water flows from the canal through this mycelial train and then into these series of aquatic tanks, and then back out to the canal onto a restorer. So it's a combination of several technologies. And that's the restorer just a month and a half ago. And there's the inside of the greenhouse. So you can see this is really full of plant life. And there's mycelium. So it's really the enzymes in the mycelium that are actually being secreted into this waste stream as it flows through the system that are degrading the hydrocarbons. So water flowing through the system removes about 95% of the hydrocarbons. The impact on the canal itself is a little bit harder to measure because it's a water body. But what we have noticed upstream and downstream effects with a reduction of 40% of hydrocarbons in sediment. And we've also really noticed that there are a lot of indicator species that are returning to this canal. This past summer we saw frogs, which have very porous skin and especially in heat cannot tolerate especially petroleum because it goes right through their skin. So this is an ongoing project that we are continuing to do research on. And another thing that we're doing at this project is hosting workshops. So we call this the Living Systems Laboratory, and we have students come really from all over the US and Canada to come and do ecological design projects with us and to actually learn how these systems are made. Launching a restorer that this group of students had made back in May onto the canal. So we're going to travel again and go to South Africa and talk a little bit about some work that we did there. So we began working in South Africa about a year ago, looking at sanitation issues in informal settlements, in the settlements that were established post-apartheid. And in particular in a settlement called Longruk, which is in the Western Cape province outside of the city of Stellenbosch. This is Longruk. It sits on a beautiful slope hillside. So in Longruk there's no formal infrastructure. There's several public taps where people collect water in buckets to use in their houses, and after they're done with this water, they take it back outside and they dump it into a series of really rudimentary canals that are flowing, or channels that are flowing down the side of the hill. This is the path of these channels down the hillside. And that water then eventually ends up in their sports field and turns the sports field into a soggy mess, and then also flows into a river called the Berg River. And this is happening all over South Africa. There are these settlements all over. And the government has become interested in finding a solution for this work because there's a lot of fruit and wine exports coming out of the city, or out of the country, and particularly this region. And the European customers of these exports are not allowing these, are not importing this product anymore because of the E. coli that's in the rivers that are being used for irrigation. So there's an economic incentive to deal with this issue, as well as a humanitarian incentive. And these are a close-up of what these channels look like. So the water that's flowing through them is really of septic quality when you look at the water chemistry. So it's the equivalent of what comes out of your septic tank. It's what is flowing out in the open on these streets. There's our engineer Max measuring its flow rate. There's the Berg River that is coming up in. So what we did was we designed a series of technologies. This is an eco machine that we designed to go right on the sports field. This technology is getting bid for the construction right now, so I don't have actual images for you, but hopefully I will soon. And it's a series of 78 aquatic cells that are just gravity fed down the hill. And when we arrived, they said, well, you can't design anything that has a pump. We said, okay. And they said, and you really can't use any electricity at all because we don't have enough of it and the wires will get stolen. And we said, okay. And then they said, well, you actually can't put anything in the system that is of any value to anyone at all. So we said, okay, we will get thinking. So what we designed, this system is actually made out of reclaimed brick and mortar that's produced right in the community with the lining to make it waterproof. And it's all gravity fed. There's no pumps or valves. And within the system, there's several economic opportunities. And this was really important to the community, and we worked with the community throughout this whole design process. And so the first thing that can happen is that when these cells get filled up with solids, which is a common occurrence in wastewater treatment, you can actually take these cells offline. You can add some extra biomass, which can come right out of the pruning of the system. And then you can plant a crop of value in it. So cut flowers are a really valuable product in South Africa. So you can plant cut flowers right into the system. And then you can take the organic matter out of once you've had a season of growing flowers, take the organic matter out and then bring the cell back online. And we also designed upstream a series of tree wells, arboreal soil makers, and micro wetlands that essentially take these canals and gutters and turn them into gardens, flowing all the way through the city, which provides treatment, which really adds a lot of green to this. This settlement has almost no soil; it's all hard pack. So we're treating their wastewater, and then also offering them. There's also an opportunity to grow fish within the system through algae. We talked about very early on. And here's a soil maker. So we're hoping to see this happen in the next few months. This to actually get built, but this is a radical change in approach to infrastructure, and this is a community that is really going from zero infrastructure to ecological infrastructure, and the community is really happy that their children aren't going to be playing in septic quality water. So there's a lot of room to actually design here because we don't have the kind of regulation that we have in the US. And then we'll come back, speaking of the US, back to the US. This is a project this is the city of Peoria, Illinois. Peoria sits on the Illinois River, and this is the land cover of the city. So as you can see, it's highly developed. And so Peoria, about 7 years ago, the EPA said, you can no longer dump your stormwater, your combined sewer overflow. So when there's a stormwater goes right into the sewers fill up, and both the sewer water and the stormwater end up in the river. They said you can no longer dump your CSO, combined sewer overflow, into the river. You need to instead build a 12-foot diameter pipe underground, taking all of this water down to the waste treatment plant. And the city said, it's going to cost $500 million. And the city said, well, okay, we will deal with this issue, but we want to come up with something else. So what's happened over the past 7 years is that they're actually going to take all their stormwater and use capture and infiltrate. So they're going to build bioswales, they're going to build rain gardens, they're going to use permeable paving. So they don't even have a CSO event, they just take all their stormwater and it goes into the ground. And then we got involved with this project because they wanted to know how ecological design could fit into this equation, because Peoria is a up-and-coming city, it's the world headquarters for Caterpillar, and they really want to reinvent themselves and have an ecological future. So this is the riverfront in Peoria. There's a lot of empty space in the riverfront. There's a lot of underused space on the riverfront. We designed really a whole series of technologies that are covering the whole length of the city. So this is a restorer with a little green line that's actually 5 miles long that runs the length of the city. We also have a couple other amenities that are ecological kind of public features. And this restorer, when there's a CSO event, because they need redundant technology in case there is water, so when there's a CSO event, the restorer will treat the stormwater, but then when there's a river water, when there's not a storm event, this restorer will just simply treat the river water. And we'll also create a whole new recreation zone for the city, so people can walk on this restorer. We also designed an urban wilds as a pilot project that there's a restorer along the bottom of it that takes one of these empty lots that you saw and turns it into a new wilds, an urban wilds. So this is really exciting. We haven't built this project yet. This is happening, but this is really an example of how ecological design can really kind of be integrated into an entire cityscape, and how we can think on a large scale about this technology. So John has been saying a lot lately that he feels like this work is really finally coming out of the wilderness. He's been doing this work for many years, and it's been very periphery, but people are really starting to understand that this work is real and important and effective. So I would like to further this thought by saying that I hope in this process, also we're heading back into a wilderness, that through reimagining our built world, we can recreate and become re-enchanted with nature's work, and that we can relearn to live as a part of and next to and within the biological and life processes that we belong to. This is really about reimagining our built world. We can create a world for ourselves where our stormwater goes back into the ground, where we have in place these massive in situ remediation projects on our rivers and streams that are remediating these legacy contaminants that we're laden with, where we're using microbial and mycelial decomposition, where our lands are coming back to life, and where each neighborhood has its own wastewater treatment plant, where children want to play inside the waste treatment plant because it's a beautiful space, and where you can grow fish, and where you can use it as a garden. I believe we really can build a new world for ourselves, and hopefully this work can provide a blueprint for that, and that our infrastructure can be a part of a living system instead of a gray and concrete system. So I hope this really gives you a good, hopeful foundation for the rest of the day, knowing that there are some pretty amazing solutions out there and that this work can only grow. And if you have any other questions, feel free to email me, Lauren at Todd Ecological. And thank you very much. I think I can take a couple questions. Yeah, in the back.
Yeah, very delighted to see these kinds of applications, and of course there's an infinite number of questions about durability and
Yes.
resilience and how they can transfer, but I don't care about any of that. What I care about, these things create jobs during construction, and then what kind of employment goes on after? In other words, how many people work these things constantly to keep them going? In a good way, by the way. I think that's a good thing.
In what?
I
Oh,
think
jobs.
it's a very good thing. I want you to.
Yeah. So on a baseline, if you were just going to operate this on just as a wastewater treatment plant, you saw that one in the beginning of Omega. There's just one person that spends probably 15 to 20 hours a week operating them. So in some ways it's low maintenance, but then once you start adding in, if you want to grow other crops in the system, if you want to actually operate a fish farm, you can start adding jobs. So there's a baseline low maintenance to these systems, but they are so capable of being expanded into economic engines, and that's something we're very interested in.
Work on that, please.
Yeah. Well, then the next guy in the room is going to be like, how many people do I need to operate this? It better not be many. So.
I know.
Yeah. Anyone else? Yeah, and the pollution.
How much is known about how the various species, oh sure, thank you. How much is known about how the various species process the contaminants? You say they're removed, but I'm curious.
Sure. There's a lot that is known and there's even more that isn't known. So what we do know is that these are not, the contaminants are not up to, they're broken down into elements. So they're not taken up by the organisms and the plants, they're actually degraded into their base elements, carbon and hydrogen. And we know that there are certain plants that are really effective at this work. We also know something about what organisms to use, but we also don't know a lot about it. But what we do know, what we can measure is obviously the influent and the effluent, and also kind of the whole wonder of ecological design is that you're trying to get as much life as possible to create an ecosystem that's doing this work. So you're kind of putting it all together, but then it's baking itself into its own pie. You know, it's like becoming an ecosystem that's dealing with a particular waste stream in unique ways, but there's loads more research that needs to be done.
And I hear you talking about, it sounds like you've been talking about chemical contaminants. Have you done any work with radioactive contaminants?
No, we haven't.
Okay.
We are very interested in mining waste and working more with mining waste and also fracking waste, which hopefully will be, in the near future we can get some funding, because there actually has been a successful, at UVM, a grad student with a toxic mining surfactant and was able to degrade it in 72 hours in an eco machine. So I believe, and we believe, that this technology is the answer to a lot of these contaminants. It takes a bit of funding to actually get these pilots built, so we're hoping to get that funding.
Thank you.
Yeah.
Thank you. Are commercial developers adopting these technologies yet? So people who are doing just normal housing and commercial developments?
Yeah, so we're building an eco machine right now for Sir Richard Branson on his private island in British Virgin Islands. My colleague Max is there right now getting a sunburn. But yes, especially institutions, the scale of this is really, a household scale is not a great scale for this technology because you need a little bit more resiliency. So once you're talking over 1,000 gallons per day of waste of effluent is really when this technology becomes really great. But we see, we have Indian tribes at their community center. Lots of schools have built these. UVM has one. There's also Berea College in Kentucky. There's the Darrow School. There's actually been over 100 of these built, most of them for institutions.
We'll take one last question.
Thanks. Biological treatment has been used by man since probably the beginning of existence, and so this is just yet another form of biological treatment. And in fact, traditional wastewater technology relies on biological treatment. And when Dr. John Todd had a pilot at both the Sugarbush and Ben & Jerry's facilities, he learned that aeration, which is a fundamental part of traditional wastewater treatment, and was needed for wastewater treatment, and that the majority of the treatment actually comes from that aeration, and that the plants in those two studies were actually only doing a small portion of the treatment. So do you have data on how much of the wastewater treatment is actually happening through the aeration, through the microbes that are actually breaking down the contaminants, and how much is happening with the plants? And then the second part is, these materials are coming in contact with pathogenic waste, and what's happening to the residuals, because any process is going to have a residual that has that pathogenic nature to it.
Right. So With pathogens, we know that I'll answer your first question first. So it's really about a diversity of treatment environments. So it's not that the plants are doing a bulk of the work. We do know what happens in each step, but if you remember the 12 principles of ecological design, it's a diversity of treatment environments. So you need an aerobic zone, you need an anoxic zone, you need the organisms that are living in these plants. You also need oxygen. You need to add extra oxygen because denitrification happens or nitrification. So you have the whole nitrogen cycle, you've got the carbon cycle. You kind of need to accommodate all of these different processes that are going to happen. And so with pathogens, they need a high oxygen environment, and we know that at a certain level of dissolved oxygen, pathogens will be literally broken down. But we also do have solids, but then, which as a byproduct, I think what you're talking about is solids. Those solids are then eaten by fish, and we talked about sediment digestion. It's these microorganisms will continue to break down these solids. So in some of our systems, we do have a solids production. You saw in South Africa, we have solids that we are expecting to accumulate, but we also are working on designs that really we do redundant solids wasting, but there's not a lot of solids production because you have such a variety of treatment that you're really, one part of the system is producing solids, the other part is breaking them down. I don't know if that answers your question.
Right, but something has to happen to the fish and the plants in the end, and they have
Right,
to
so
be touched with pathogenic material.
Well, but the E. coli and the fecal coliform is actually degraded into another substance. It does not remain as E. coli and fecal coliform within the system. So because we know that there's a way to, they can't survive. They die off in high oxygen environments with exposure to sunlight. Yeah, you're welcome.
Thank you, Lauren.
You're welcome. Thank you very much.